Every modern AI relies on dense word vectors. But this architecture didn't emerge during the deep learning boom. It was engineered in 2003. That year, Bengio and his team published a neural probabilistic language model. The paper achieved two things at once. It learned to predict the next word in a sequence, and it used that predictive task to simultaneously learn a distributed, continuous vector representation for every word in its vocabulary. The shared lookup table built to hold those vectors, matrix C, is the exact mathematical blueprint that a model called word2vec would inherit intact 10 years later. But Bengio's model had a physical flaw. A massive computational bottleneck nearly crippled the entire architecture. This timeline and chart trace that bottleneck. By the team's own diagnosis, the final output layer of the network was so mathematically inefficient it consumed 99.7% of all computation. Decoding this single paper reveals how modern embeddings actually work and exposes the exact physical constraints that forced the invention of word2vec. To understand why a new architecture was strictly necessary, we have to look at the state-of-the-art in 2003, N-gram models. These models predicted language simply by counting how often exact word fragments appeared in their training data. The problem with counting is a mathematical trap called the curse of dimensionality. If your vocabulary size is v, and you are looking at sequences of length n, there are v to the power of n possible word combinations. Because that number is astronomically large, the direct consequence is that almost no sentence you test the model on was ever actually seen during training. This grid animation shows how an n-gram model handles symbols. Take two sentences. The cat is walking in the bedroom, and a dog was running in a room. An n-gram views the words cat and dog as isolated, completely disconnected nodes. Because it has no mathematical concept of similarity, the n-gram cannot transfer probability between cat and dog. If it hasn't explicitly counted the exact phrase, a dog was running, it has no mechanism to infer its likelihood. N-grams attempt to patch this flaw by falling back to a generic, unhelpful probability floor for unseen sequences, rather than recognizing semantic patterns. Counting discrete, rigid fragments scales poorly and fails to capture meaning. Language requires a geometry that understands when two words mean roughly the same thing. This continuous coordinate space illustrates Bengio's solution. Instead of treating words as isolated, discrete symbols, he assigned each word a distributed representation, a continuous vector in a mathematical space called R to the M. Notice how cat and dog physically move to cluster tightly together. The dimension m, usually between 30 and 100 features, is drastically smaller than a typical 17,000 word vocabulary. The model is forced to compress meaning into a dense space. The second necessary component is a joint probability function, denoted as g, that operates directly over these continuous vectors. Because this function is mathematically smooth, a small shift in the coordinate space yields a small change in probability. Words physically near each other produce nearly identical predictive scores. This yields a combinatorial payoff. Observing a single sentence in training physically moves the vectors for its words, and through mathematical smoothness, that adjustment updates the probabilities for an entire neighborhood of similar, unseen sentences. The vectors and the probability function must be trained simultaneously. The word vectors only develop semantic geometry because they are constantly tuned by stochastic gradient descent to minimize the error of predicting the next word. Bengio turned the curse of dimensionality into a weapon. By relying on spatial geometry instead of exact discrete matches, the model generalizes from sparse data. So, where do these continuous vectors physically live in the computer's memory during the forward pass? This block diagram represents the paper's core artifact, a single shared lookup table called matrix C, with dimensions equal to the vocabulary size, v, by the vector size, m. Matrix C contains zero nonlinearity. Embedding a word is literally just indexing a row in this table. It requires zero multiplications. To make a prediction, the vectors for the preceding context words are extracted from matrix C and concatenated into a single flat input vector called x. This input vector x then flows into a nonlinear hidden layer using a hyperbolic tangent, or tan, activation function. The specific math for this hidden state is A equals tan of D plus H times X, where H contains the layer's weights. The architecture also includes an optional direct linear bypass, W times X, allowing the raw context data to skip the nonlinear tan layer entirely. The outputs from both the hidden layer and the direct bypass sum together to form Y, the unnormalized output vector. This output vector contains a distinct predictive score for every single word in the entire vocabulary. Finally, a softmax function normalizes those raw scores in Y, guaranteeing they sum to 1 and form a valid probability distribution for the next word. This equation 1 block, a 2-layer multi-layer perceptron, successfully beat the heavily optimized state-of-the-art n-gram models on perplexity benchmarks. This exact sequential logic, pulling a linear lookup, passing it through a nonlinear hidden representation, and projecting it to an output, forms the structural backbone of every neural language model running today. Despite the mathematical elegance, the model hit a physical wall. To train on the AP News corpus, Bengio's team required a cluster of 40 CPUs running for 3 weeks, and they only completed 5 epochs. The problem lies in the architecture's scaling asymmetry. The matrix C lookup and the tan hid hidden layer are highly efficient. They are computed only once per context window. But the final output layer is order V. It must calculate a unique score for every single word in the vocabulary, roughly 18,000 times, for every single training example. This stacked bar chart visualizes the computational cost. Because the hidden dimension and vector dimension are tiny compared to a typical vocabulary, the output projection dominates the parameter count. Bengio's paper quantified this explicitly. The flat softmax operation over the entire vocabulary forces the output stage to consume exactly 99.7% of the total computation. With a nearly impossible compute bottleneck, how did the team viably train the input matrix using stochastic gradient descent on millions of words? The saving grace of the entire architecture is the structural sparsity of the matrix C update. This grid represents the massive matrix C. During a backpropagation step, the gradient for this matrix is 0 everywhere, except for the specific n-1 words currently present in that exact context window. This scatter-add update meant the system never had to read or write the full matrix to memory at once, preserving critical bandwidth. Structural sparsity knew the continuous embeddings updatable in real time, but the crushing weight of the 99.7% output wall acted as a hard physical ceiling on the model's ability to scale. Bengio's team was highly transparent about the model's physical limits, specifically citing the order V output wall. This image from section 5.2 of the 2003 paper, the Future Work section, operates as a prophetic diagnostic manual. Bengio explicitly suggested organizing the vocabulary into a tree structure or using an important sampling speedup to bypass the crippling cost of the flat softmax. We jump forward exactly 1 decade to 2013, when Thomas Mikolov introduces word2vec to the world. Word2vec did not invent the continuous embedding matrix. As this animation shows, Mikolov performed aggressive architectural surgery on Bengio's 2003 design. Word2vec inherits the shared matrix C and its sparse gradient updates, completely intact. To achieve massive scale, word2vec deletes the nonlinear hidden layer and replaces the flat softmax with Bengio's exact suggestions: hierarchical softmax, which is the tree structure, and negative sampling, which is important sampling. The 2003 Neural Probabilistic Language Model engineered the continuous vector geometry that powers AI today, and it wrote the exact architectural to-do list that allowed the next generation to scale it to the world.